In this video, I will talk about the stability of finite volume method. Previously, we saw that we can use Taylor series to find out the consistency. So here we will see the stability. Remember that to find the stability, we need some tools. The first tool that we have is called the Fourier analysis. It is a very famous concept in mathematics. And the second one is the energy method. You find out the stability with the energy method. The third method to find the stability is the normal mode analysis. Normal mode analysis. These are the three methods where we can use the stability. We can use to find the stability of numerical method. Remember that these methods, as I repeated earlier, and I can repeat here as well, these are for finite difference method, and finite difference method is finite volume method when we have the order of numerical method is 2. Okay, so we will not talk about the energy method and normal mode analysis since it is a bit technical, but most of us probably know that what is Fourier analysis. Fourier analysis is the mathematical concept where a function can be written in terms of sine and cosine, combination of sine and cosine. Fourier actually told us in the history that you can write any function which is periodic can be written in the form of series form. So according to him, here I talk about the Fourier analysis. So our topic is the Fourier analysis. Fourier analysis. So a Fourier tells us that you can write any function in sum of sine and cosine, where I is equal to 0 to n minus 1, and there is a amplitude, for example t hat L maybe, e raised to power iota 2 pi L x j. This is the Fourier series, but it is written for the discrete form since we are working in numerical method. Remember that here we have generated points with xj is equal to j delta x, and where j is from 0 to n and delta x is 1 over n. This is our assumption. And in Fourier analysis, we also have one assumption which is called the periodicity. So it means that whatever comes in will be equal to whatever goes out, that will be equal to each other. This is periodicity. And here you can see that this is amplitude. In Fourier analysis, if you know the Fourier analysis, you know that on the coefficients we had a0, not a0, maybe a0, yes, an, bn, and cn. Here we are calling that t hat, okay. Then we have iota. Iota is a complex number. Xj is the discrete version of continuous variable x, okay. And on the left hand side we have tj, that will be tj, and j will be equal to 0, 1, n minus 1. So that's how we write the Fourier modes. These are called Fourier modes. Here, k is probably k is not visible over here, but k is this value over here. It is called wave number. The k is called 2 pi l, which is a wave number. And t hat, when we write this in terms of wave number k, then we can write t hat l is equal to t hat k. Okay, so we put that value over here. Another thing we notice that lambda is equal to 2 pi over l. Lambda is 2 pi over l. So using all these equations, we can write this as t j, that will be equal to k t hat k e raised to power iota, and we replace this 2 pi l with k, which is kappa, and this we have xj, and j will be equal to 0 to n minus 1. Okay, remember that when we have, for example, 3 grid points, when we have 3 grid points, then there are 2 cells. That's why when we have n number of n plus 1, n plus 1 grid points, it means that we have n cells, n cells. So from this we have simplified over this a bit complicated Fourier modes into the simpler one. Here it is the summation. Since in Fourier analysis we write all the equations, uh, all the terms in series form. So what we have, k will be equal to 0, 2 pi and 2 pi n minus 1. Since wave repeats after every 2 pi. The first wave reaches over here at 2 pi, then we also have 4 pi, then we also have 6 pi, and so on. Okay, so this wave actually repeats itself. Then we have the coefficients. When you expand that, then we get e raised to power iota k x0. When j is 0, then we have e raised to power iota k x1, for example. Then we have e raised to power iota k x2, and then at the end e raised to power iota k n minus, xn minus 1. These are the vectors. Okay, so what we have, when we put this method, this series into the numerical method, we actually get t hat n, maybe I write over here, t hat n k, and there will be amplification factor. Probably you don't understand this now, but when I apply this to particular problem, then it will be clear. For example, we get g k delta x delta t, and that will be, and this amplification factor depends on t, and then we have t hat 0 k.